Hi, my name is Shibli Barua, and this is a short presentation on chemical equilibrium that is meant for freshman chemists in a four-year college or university. So we begin with the difference between predominantly forward reaction versus reversible reaction. So the first example that you see on the screen is of a predominantly forward reaction where we have sodium hydroxide as a base reacting with hydrochloric acid to give us sodium chloride salt and water. Now the reason why this reaction is predominantly forward reaction is because the reactants combine together, react together to give us products, and we don't expect the products to combine back to give us reactants. On the other hand, if we look at the next reaction, which is described as a reversible reaction, and it is denoted by this sign, reversibility sign, we have methane gas reacting with water vapor to give us carbon monoxide and hydrogen gas. Now we have the reactants combining together to give us products, and at the same time we have the products combining together to give us back the reactants. So basically the reaction can go in both forward as well as backward direction, the reverse direction. So that's why it's a reversible reaction. Now having said all that, now we're going to move on to the concept of reaction quotient, which is described as QC or symbolized as QC. Now the reaction quotient QC gives us a quantitative relationship between the concentration of products and the concentration of reactants in a chemical reaction. Now if we consider the general reaction where we have reactant A reacting with B to give us the products C and D. Now the small letters A, small letter B, C, and D, those are the stoichiometric coefficients that balance this chemical reaction. Now in order to represent the QC, the reaction quotient, we write the concentration of the products up in the numerator, and then we have the concentration of the reactants down at the denominator, and each concentration is raised to the power of the stoichiometric coefficient from the balanced chemical equation, as you can see. So C, capital C concentration has been raised to the power of small c, capital D concentration has been raised to the power of small d, and so on and so forth. Now, from this expression we can see that if the product concentration, or if the numerator, is greater than the denominator, then the QC value is going to be greater than 1, which means we have more products in the system than reactants. Now if QC is less than 1, then obviously we will have less products in the system or more reactants. Next we will look at a few examples of reaction quotients. We will take specific examples and we will see how these three reactions in particular, how the reaction quotients for these three reactions can be expressed. Now we have in the first case methane reacting with water vapor once again to give us carbon monoxide and hydrogen. And look at the QC expression we have is the same as we have defined in our earlier slide. We have carbon monoxide, hydrogen gas raised to the power 3 because we have a coefficient of 3 up there, divided by the concentration of methane and concentration of water. And carbon monoxide, methane, and water, they all have a coefficient of 1 in the balanced chemical equation up there. Next we have an interesting case. We have calcium carbonate decomposing into calcium oxide and carbon dioxide. And as you can see in the reaction, calcium carbonate is a solid as well as calcium oxide, which is a solid, but carbon dioxide is the only gas. And we see that the QC expression is only concentration of carbon dioxide. And that is because the solid calcium carbonate and calcium oxide, we say that their concentration or their density remains constant throughout the reaction. Their amount changes, their amount decreases as the reaction progresses, but their concentration or density remains the same. And that's why they don't contribute to the QC expression, because their concentration is a constant. Now we see a similar pattern, similar case with pure liquid or water in the third example. So in this case we have the QC expression as ammonia concentration up in the numerator divided by nitrogen dioxide concentration and hydrogen concentration down in the denominator, and the concentration of water is missing because water is a pure liquid and the concentration change of water is negligible, that's why it's assumed to be constant, and that's why it does not contribute to the QC expression. Now what we're going to try to do is we're going to try to define the concept of chemical equilibrium, as well as we're going to define equilibrium constant. So a chemical reaction is said to be in a state of equilibrium when the rate of forward reaction is equal to the rate of reverse reaction. By that what we mean is the rate of forward reaction means the rate of formation of products, and the rate of reverse reaction means the rate of formation of the reactants. So if we consider this expression once again, methane with water vapor, we can express, well, it's QC as this expression, but at equilibrium, the QC is named or is termed as Kc, or the equilibrium constant. Now if a system is not at equilibrium, we call this as QC. If the system reaches equilibrium, we change the name of QC to Kc. We symbolize it as Kc. Now at equilibrium, the concentrations of products and reactants, they remain constant, they remain unchanged. And that kind of makes sense because at equilibrium, the rate of forward reaction and the rate of reverse reaction, they're the same. So the concentrations are not gonna change. They're gonna remain constant. Now what we're gonna do is we're gonna look at the relationship between QC and Kc, or how QC and Kc can be related, and how we can predict the direction of a reaction by comparing the QC and the Kc values. So the basic concept is every reaction tries to achieve equilibrium, tries to be in a state of equilibrium by either shifting to the left or to the right. What do we mean by shifting to the left or to the right? By shifting to the left, the products go towards forming reactants, and by shifting to the right, the reactants go towards forming products. Now if we have the QC value greater than the Kc value, that means the reaction quotient value greater than the equilibrium constant value, it tells us that the system, the reaction system, has too much product, or the concentration of the products is too high. And that's why the reaction would shift to the left. That means it needs to get rid of those excess products so that it can form more and more reactants, so that the QC value can come down to the Kc level. Similarly, if we have QC less than Kc, that means we have too little products in the system. That means we need to replenish the amount of products so that we can achieve equilibrium once again, so that QC can be equal to Kc. And in order to do so, we have to have the reaction shifting to the right. That means the reactants should react more and more to form more and more products. Now, if the system is at equilibrium, we have already said that QC will be equal to Kc, and the concentrations are going to remain unchanged or constant because the system is in a state of equilibrium. Now let's look at a specific example. So let's look at a problem where we have dinitrogen tetroxide gas decomposing into nitrogen dioxide, as you can see on the screen. Now we have been given some values. The Kc for this reaction is given as 0.21 at a temperature of 100 degrees Celsius. Now at any point during the reaction, we have dinitrogen tetroxide concentration as 0.12 molar and nitrogen dioxide concentration given to us as 0.55 molar. Now the question is asking us, is the reaction at equilibrium at this point? If it is not, then which direction should it progress so that it can achieve equilibrium? Well, the first thing to do is to find out what QC is. Well, the QC expression from the balanced chemical equation, we see that it's concentration of nitrogen dioxide raised to the power 2, or concentration of nitrogen dioxide squared, divided by concentration of dinitrogen tetroxide. Now if we start plugging in the values, we find that QC equals 2.5. Now QC equals 2.5, when we compare it with Kc up there, we see that QC is actually bigger than Kc. And that tells us that we have too much product, or the concentration of products in the system, concentration of nitrogen dioxide in the system is too high for us to reach, for the system to achieve equilibrium. And that's why the reaction needs to shift to the left so that it can get rid of excess products and form more reactants, so that QC value can come down to the Kc level. And the equilibrium will be achieved when QC equals Kc, and the reaction needs to shift to left. That means it needs to form more reactants from products. So having said that, now that was the last example. So that's so in order to wrap things up, we're going to summarize what we have talked about so far. So first, we have discussed the reversible reactions. We showed the difference between predominantly forward reaction as well as with reversible reaction. And then next, we talked about reaction quotient, or QC, and we have seen the expression for QC from a balanced chemical equation, how we can express QC with the products up in the numerator and the denominator containing the reactant concentrations. Then we looked at reaction equilibrium, and we discussed equilibrium constant, which is Kc. And finally, we compared the QC and Kc values, and we predicted which direction the reaction would shift in order to achieve equilibrium. And then we have looked at a specific example where we had dinitrogen tetroxide decomposing into nitrogen dioxide gas, and we determined by calculating QC value, we determined which direction the equilibrium will shift in order to achieve equilibrium, or in order to make QC value equal to Kc. Thanks for being with me. Thanks for listening. You have a good day.